I will now tell you about one of the hallmark results in quantum mechanics, the celebrated Heisenberg uncertainty principle. It states that for any state psi of a quantum particle, at any moment in time, the product of the uncertainties in the particle's position and momentum cannot be less than half of h bar. The uncertainty principle establishes a fundamental limit on how precisely we can simultaneously know a particle's position and momentum. The more certain the outcome of a position measurement, the less certain the outcome of a momentum measurement, and vice versa. In other words, creating a physical scenario with a small uncertainty in the particle's position will inevitably result in a large uncertainty in its momentum. This means that, contrary to classical intuition, no matter how advanced our measurement tools become, we can never measure both properties with arbitrary precision at the same time. Let me explain where the Heisenberg uncertainty principle follows from. In fact, we've already acquired enough knowledge of quantum theory to construct a proper proof of this principle. First, we'll take the difference between the position operator x hat and the position expectation value x mean, and apply this difference to the particle's wave function psi. Second, we'll do the same thing with momentum instead of position. Third, we'll multiply the first expression by a real number u and the second term by the imaginary unit I, and add the results together. Then, we'll take the modulus of the whole expression and square it. Finally, we'll integrate the entire thing over x. The value of the expression we've obtained at the end of this process depends on the value of u. Therefore, considering u as a variable, we can regard our expression as a function of u. Let's denote this function by f of u. Just as a reminder, when the position operator, x hat, acts on the wave function psi, it simply multiplies psi by x, while the momentum operator, p hat, operates by differentiating psi with respect to x and then multiplying the derivative by minus I h bar. By construction, the function under the integral is non-negative. Consequently, the integral itself, and thus the value of the function f of u, is non-negative for all u. We will soon utilize the non-negativity of this function. By evaluating the integral over x and considering the definitions of the position and momentum uncertainties, delta x and delta p, you can show that the function f is a second-degree polynomial with the following coefficients. The coefficient in front of u squared is the square of delta x, the coefficient in front of u is minus h bar, and the constant term is the square of delta p. The detailed steps of this calculation are left as an exercise. Please work through this exercise carefully. As always, step-by-step solutions are provided. So, let's summarize what we found. We have a parabola with coefficients delta x squared, minus h bar, and delta p squared. And we know that this parabola must be located in the upper half plane, since f is non-negative for all u. Analyzing the coefficients, we find that the parabola is centered at h bar over 2 delta x squared, and the value of f at this center point is delta p squared, minus h bar squared over 4 delta x squared. From this, it follows that the function f is non-negative everywhere, if and only if delta p squared is greater than or equal to h bar squared over 4 delta x squared. Taking the square root of both sides, we arrive at the Heisenberg inequality. The product of delta x and delta p cannot be smaller than half of h bar. This concludes our derivation of the uncertainty principle. Please carefully review the exercise accompanying this lesson to go through each calculation step and ensure you fully grasp the proof of this important result.